Okay, so far we've seen how we explicitly handle references where the user has to deal with all the memory management themselves. And now I want to talk about implicit reference handling. It's essentially like going from C to Scala, say. Right, so before we have, if we wanted to do any of our references, we'd have something like this, right? Let x equal a new ref of, say, 1, and then in let y equal a sign ref x15 in dref of x. So what does this do, right? The new ref places the value 1 into an empty memory cell and then returns a reference, which is a value, right, a reference with an address in it, and binds that to x in the environment. Then this line, right, assign ref, looks up where x points to in the memory and then rewrites that cell as 15. And then we end up binding 15, the value, to y, as assign ref's return value is always whatever is the value we're binding it to. And then we deref x, which means we look up in a memory cell that x points to and just return that value. But I don't necessarily want to do this. This feels a lot like working with pointers in C, something that's always sort of a pain unless you really enjoy that kind of thing. Instead, I want to do something more like Scala, right, where I can do something like var x is equal to 10, x is equal to 15, var y is equal to x, and then we do maybe like x minus 45, right? In this var statement here, right, remember in Scala we have vals, which are just like our normal let statements that map to the environment. They're immutable. We can't change what they are. We can change what they mean in different scopes, but that never actually gets rid of that val in that particular scope, right? It just changes the meaning of that, changes the scope of the value, right, of the environment. Then we also have vars, which are mutable, so we can change their value. That's exactly what we're doing here. So this is sort of an implicit new ref, right, of 10. This change is something like an assign ref, right, x to 15. This is another new ref of dref of x. Right, so we're actually coming up with a new memory location, and we're taking whatever x was value is in the location that x points to, and binding it to this new variable y. And then this is a dref of x, right, minus 45. So this is what is sort of going on under the hood implicitly, right? That's why we're calling this the implicit form, because all of this stuff is happening. It's just that we have a different concrete syntax for dealing with it. And we'll have a different little bit of abstract syntax too that we'll go through. So let's see how we would write this up in Lattice as with implicit references. Right? So we would have something like let var of x equal 10 in let dummy equal assign ref x 15 in let var y equal x in x minus 45. So again, what happened? We have implicitly we're making a new ref right here, and we're going to use this new keyword let var in order to do that. Right, so instead of normal let, we'll have this new keyword let var, and it basically does the new ref for us. And then we're still going to need an assign ref style thing because we don't really have any other language in our in Lattice in order to be able to do these reassignments. So we'll still have an assign ref x15. It's going to return 15 as its value as an expression, and we're just going to bind that to a dummy variable in order to make sure that this happens as a side effect. Then we have in let var y, so we're making a new var here, And the secret little bit here is when x is on the right-hand side of an equal sign, it's going to automatically deref that, right? So we're going to get the value that x points to. Likewise, down here we have a automatic deref. So that's what's going on, right? We have no user level deref, no user level new ref. We still have an assign ref because that's a special kind of thing that we need for this, but everything else is handled under the hood. And all of this should work with the exact same store technology that we came up with. So if you remember, it's an infinite list. We're not thinking about any memory like management issues of overflowing our memory. And it's labeled by the natural numbers as addresses, and then we have values in here. And we have create cell, assign cell, and lookup cell. Right, create cell will find the first empty cell, put whatever value we have in there, and then return the address of that cell. Assign cell will look up the cell with the corresponding address you gave it and change the value to whatever value you gave it. Lookup cell will just look up the address that you gave it and return the value that's in there. So all of that's the same. We're just changing the concrete syntax and the formal syntax to really be more like Scala than it is like C. So let's look at another example. Let me show exactly what this example would look like in our old style, right? So just to be very clear here, right? This would be x equals with explicit references, right? So let var x equal 10, that should be x equals new ref of 10. And well, we're going to do this assign ref. That's basically the same, right? So let dummy equal assign ref of x and 15 in. And then this one is, right, let y be new ref. And then what does it take on the inside? This x here, which is going to be dref of x. In dref of x minus 45. Right, so this is the explicit reference form. This is the implicit reference form. All right, let's look at another example. Let var x equal 15 in let f be a function that takes in a z and returns z plus x in let y equal assign var x to 20 in f of 20. Now, what's going on here? This one's maybe a little tricky. So we've made a new reference to a new reference with let var x and bound that to 15. So let's assume it's over here, right, in our address 0 memory cell. And then we make this function, right, that takes in a z and it's going to add z to x. And then we're going to reassign the var or x to 20, right? We'll bind that to y as a dummy variable. But the important part is that we've changed this over to 20. And then we call f with an input of 20. So what should this return? Well, what is inside the function, right? So 20 is going to get mapped to z, and we're going to, so z is 20. But what is x? Right? X is a reference, And so when we see x like this, we're going to just deref x and look in the store that's current, right? It's not the store that happened when we made the closure of the function. The closure of the function only contains the local environment that says x points to cell 0. So what we end up doing is we're adding whatever happens to be in cell 0 at that time. So we'll actually end up with this final answer will be 40. Right? So this is a way that we can kind of get around our static scoping kind of things, right? Which is by, without changing anything about function definitions or closures, right? Just the fact that x is now not just a variable, or not just a name in the environment, right? But in fact, it's pointing to a reference to this box that can change. That f ends up looking up x, being like, oh, what's the current change there, right? If we change this, so let's suppose we didn't have the let var, so we have just let x equal 15, right? Then and then we let f be the function that takes z and returns z plus x. Well, now when we create the closure for f, x is just bound to 15. And so, I mean, we can't quite do this assign var, but if we made a new x, right, let x equal 20 in f of 20, the x up here, right, so this x shadows this x, the x that got captured in the closure here is this first x, so we'd end up with 20 plus 15, or 35. So you can see that with this implicit, I mean, we could do this with the explicit as well, but this lets us sort of get around the static scoping issues that you might, I mean, I don't know if it's an issue so much as something that you might want to be able to do, right? You might want to have a little bit more flexibility when it comes to what does my variable mean on the inside of my function. So we're going to show how this can just naturally fall out of our new definitions of our implicit reference world, right? So this shouldn't be too surprising, but it's definitely a little weird. In fact, Scala does this too, right? So this is same as Scala. You can try that out if you like to see exactly what happens. But it's the same process. If you have a var on the inside of a function that was defined outside, you can change that var and the function will register those updates, right? Because the closure only contains the fact that that's a pointer to a memory cell. The actual location of the memory cell isn't saved at the time that you make the closure. So what do we need to add to our language in order to make this work? Not too much, right? The only two things that we really saw here were we need a let var statement, right? This is going to take a string, which is going to be our keyword, or our variable name, and then we'll have two expressions, right? This is going to be the left or the right-hand side of the equal sign, and then this is going to be the rest of it, the body, the bit after the in, right? And then we're also going to need an assign var, which is going to take in a string and an expression, right? And we're going to look this element up in our store and then put whatever expression evaluates to into that location. So let's see how we would translate some of our concrete lettuce into the abstract lettuce with these two new things, right? So we have expression can be one of these two guys, plus all of our other, lettuce stuff. So let var x equal 15 in x plus 35. So how would we write this up in abstract syntax? It's going to be a let var. We have a string that should be x. Right, we have a expression which is going to be this 15, so const 15, and then this other expression which is in the body, which is going to be this, right? So plus ident of x const 35. Right, so these two are equivalent. This is our concrete and our abstract. Let's do it again with maybe a little more complex one. Let var x equal 20 in, let dummy equal assign var x35 in x. Okay, so this uses one of our assign vars, so we'll see how that shows up. But right, same thing. This is going to be a let var statement. So let var and then x 20 const 20. And then this let statement, right, that's a normal let statement, which is going to be dummy in quotes because that's our variable name, and then we're going to have an assign var as the right-hand side of the equal sign. And what does an assign var take? It takes in the string name, which is going to be x, and it's going to take in the expression that we want to bind it to, which is going to be const of 35. And then we need whatever is after the in our let, which is just going to be ident x. And 1, 2. Yeah. Okay. So one term that is thrown around a lot in this, which comes from C and C++, is what's called an L value and an R value. I mean, this is basically for left and for right, and the idea is if I have x, right, x equals 10 versus, say, y equals x, right, x is on the left-hand side here while x is on the right-hand side here. And the meaning changes if x is one of these implicit references. And we can kind of see that, right? If we look over in this code, I have x on itself here, right? That's on the left-hand side. This is on the left-hand side of these terms. And we can see in our abstract syntax, we have x just in quotes and x just in quotes there. Similarly, right, we have this x, which corresponds to this x over here, right? This one has been wrapped in ident, and this is essentially on the right-hand side. This is an R value. So these pink ones are L values because they're generally being assigned to, and we can sort of tell the difference in our abstract syntax because x's, they're just strings, while the R value over here is relates to an ident. We can see the same thing over here, right? So here we have an R value, we have an ident of x, and here we have an L value, which is a just plain old x in a string. So in general, we have these are declarations, and you know, they're the locations to be assigned to, really, right? And then this is really sort of a deref, automatic deref form. Right, this is a value in the memory. So I'm not going to use L value and R value much because I'm not that strong of a C coder, and I prefer to sort of think about exactly what's going on here. But if you're going to learn programming languages, you should know these terms, and they basically they work in this sense. So we can see where the L values and R values are in our abstract syntax. You could also tell in the concrete syntax, but it's much clearer in the abstract form. Let's look at one last example. Which is going to be let var x equal 10 in, let y equal 20 in, let var z equal x plus y in, x plus y plus z. Now, which ones are the L values and which are the R values? Right, well, this is an L value, and C is an L value here. And those are the only two L values that are being assigned to, right? They're the only times a full variable, right, a reference is being assigned to. The Y's don't really count because they are just sort of these environmental vals. So they don't really have that, that separation and definition because there is no sense of I have to automatically deref this. Where are our R vals, right? Well, this is an R val, this is an R val, and this is an R val, right? Because they are sort of implicit, they're being implicitly derefed in this situation, right? So when we walk through our evaluator, we'll see how to naturally handle this to be able to get the values that X refers to as opposed to accidentally adding a bunch of references together. All right, I think that's all I wanted to show you for the background stuff. Next, we're going to talk about the semantics of implicit references.